So our next speaker is Dr. David Luxat. Dave received his PhD in theoretical condensed matter physics from the University of Toronto. He is currently working at Sandia National Laboratories, leading efforts in developing nuclear safety and risk assessment methods, strategies, and codes. He has a background of work in severe accident analysis and developed a number of models, including notable analysis of the Fukushima Daiichi accident in 2011. He leads the Severe Accident Modeling and Analysis Department, which develops the MELCOR code for the NRC. Today he will be giving a talk on MELCOR activities with molten salt reactors. Take it away.
Before I start in, I wanted to acknowledge all the contributions from a number of people who are part of our MELCOR team here at Sandia. Larry Humphreys is the lead code developer for MELCOR, and he's been ably leading this team for a while now, and it would be remiss of me not to give a very strong nod to Larry for all of his efforts along the way to get us to the point of having these capabilities. Brad Beeney has been leading a large number of non-LWR code developments activities for MELCOR, and Fred Galbart in particular has been leading the development of a new model that we've added to MELCOR, specifically intended to treat fission product thermochemistry in these non-water working fluid systems. And we'll get to a little bit of that. It's kind of an exciting addition to MELCOR that actually flanges up a lot with what Ted was just talking about, and certainly it's been a valuable interaction with Ted in that regard. So without further ado, I'll move on to I hope I can move on. Let me see to the next slide. So the work that we've been doing with MELCOR, and I'm going to try and sort of just frame what we've been doing with MELCOR in terms of the overall activities that the NRC is engaged in to develop the necessary analytical capabilities to be ready to review and to assess new types of reactor systems being proposed for deployment in the United States. The work for MELCOR, and the NRC has essentially developed a near-term implementation action plan to essentially develop the regulatory readiness to enable a number of key national priorities related to the development of advanced nuclear energy technologies. The work we've been doing with respect to MELCOR really falls under Strategy 2 of this near-term implementation action plan, which is focused on the development of analytical tools. The specific work that we've been doing actually has been guided by a number of in particular, two specific volumes that lay out the strategy, that lay out strategy number 2. There have been a number of volumes developed by the NRC to lay out the process by which they will be developing the analytical capabilities needed to regulate advanced reactors. They range all the way from DBA type analysis capability needs to off-site emergency response capability needs to fuel performance needs. Where we're situated with MELCOR is really in what is volume 3, which is the assessment of or the analytical capabilities needed to assess accident progression and radiological source terms and associated consequences due to postulated accidents in these reactor systems, in particular beyond design basis accident scenarios. MELCOR also comes into play with respect to another volume, another component of the analysis needs to assess safety in these new reactor systems. That's volume 5, which actually focuses on the analytical capability needs specific to understanding safety under events in a various number of stages, if you will, in the fuel cycle for these advanced reactor concepts. The work that I'm going to be talking about in the rest of this talk really flows out of Volume 3. We're just actually starting in on the work related to the non-LWR fuel cycle. But the work we've been doing here, and that I'll describe, is really focused and really comes out of demonstrating readiness to assess safety in reactor systems. We've had a number of, if you will, a lot of work, a lot of concerted effort over the past couple of years to get some of the additional capabilities to MELCOR to assess accident progression source terms in these non-LWR advanced reactor systems, and that's culminated very recently in a number of demonstration activities that we've used, if you will, to shake down the capabilities that we've been adding to MELCOR, but also to demonstrate, if you will, the level of readiness in these capabilities. These demonstration calculations that we've been doing have focused on, in this fiscal year, essentially FY20 government fiscal year 21, have focused on 3 specific advanced reactor systems. We've had a very valuable collaboration going on with the SCALE team at Oak Ridge to essentially show the integrated capabilities to do an accident progression and source term calculation for fluoride salt-cooled high-temperature reactors, a molten salt system with triso fuel, for a heat pipe reactor, an INL Design A heat pipe reactor, and also for a high-temperature gas-cooled reactor, a pebble bed high-temperature gas-cooled reactor. We've done a number of studies to demonstrate overall capabilities to analyze accidents in these systems. I'll focus in this talk on the FHR, obviously, but I didn't want to, if you will, move on before essentially highlighting the breadth of capabilities and the generalized capabilities that are in MELCOR for assessing a broad range of reactor systems. Importantly, one of the things we've done for the heat pipe reactor and the high temperature gas cooled reactor specifically was we've actually done uncertainty studies and to exercise the code and to demonstrate its readiness to essentially perform thousands upon thousands of studies, if you will, given that uncertainty may be a very critical thing to probe into for non-light water reactors, given that the data is still evolving. As we look forward to fiscal year 22, we're looking at two additional systems for which we are going to be demonstrating MELCOR capabilities, and if you will, rounding out the capabilities in MELCOR to be able to simulate these systems. The nearest term system that we're looking to work on in the next couple of months and have a reference plant model done is actually the molten salt, the liquid-fueled molten salt reactor. We actually already have an MSRE model that we've developed a couple of years ago and that we've done some initial benchmarking with, but we're going to be applying that model, if you will, to demonstrating more of the capabilities in MELCOR and the ability of MELCOR to simulate a broader range of accident scenarios. More towards, if you will, the middle of this fiscal year now, we're also going to have a plant reference model done and available for the sodium cooled fast reactor. And we'll have subsequent, if you will, demonstration calculations available for that. Now, MELCOR itself, and I wanted to now shift from this sort of overall view to begin to dive in and begin to, if you'll peel away some of the philosophy around how we approach MELCOR and how we approach modeling and simulation, safety modeling and simulation with MELCOR. It's important to note, and this is something that I really need to note here, is that MELCOR has really evolved from, really since 3 Mile Island, MELCOR has really, if you will, built itself up out of the significant investment in the United States to better understand the level of safety in existing light water reactor systems. Following 3 Mile Island, there were a large number of studies conducted to better understand what the level of safety in light water reactor systems was, what the potential consequences, the potential risk to the public from the light water reactor power venture truly was. And as part of a lot of this experimental effort, this really extensive experimental effort to understand a range of accident phenomena, came MELCOR. MELCOR has actually affectionately or often been called in the past, if you will, a repository for the state-of-the-art knowledge in accident, in nuclear energy or nuclear energy system accidents. And so MELCOR, through this long progression, has really built up, if you will, a breadth of capabilities that reflect, if you will, our state of knowledge about a range of physics and chemistry that happen in particular in light water reactor systems under accident conditions. But the phenomena is actually quite general. And it's actually enabled us to begin to turn our eyes to meet the challenge that we're facing now, to begin to have the capabilities to assess safety in these advanced reactor concepts. And so with MELCOR, we're really turning beyond and turning away from, if you will, what we've traditionally done up to 2010, which was try to understand what is the level of risk associated with the light water reactor power venture, to understand or to apply this capability to really help, if you will, enable the nation to understand safety, and in particular the NRC to understand the level of safety associated with a broad range of proposed near-term advanced technologies, as well as longer-term advanced reactor strategies. So MELCOR has been applied, has been developed for not just if you will, traditional operating light water reactors. It was used in assessing the NuScale small modular reactor, both by NuScale and by the NRC. And it is also under current development and application with respect to understanding the safety benefits and the safety implications associated with advanced accident-tolerant fuels like iron, chromium, aluminum, etc. Beyond that, we also have, as I was saying, have been building in all these capabilities in MELCOR that leverage this foundation of physics and chemistry that already sits in MELCOR to begin to apply it to essentially the spectrum of advanced reactor concepts that we see. Now, MELCOR is really and has lent itself, if you will, to being able to apply itself in a more flexible manner to analyzing these types of systems, because it has bundled into it essentially a broad range of physics that we see across all reactor systems. And so we often think of MELCOR not as, if you will, a generalized numerical framework for solving different classes of partial differential equations, if you will. We think of MELCOR more as, if you will, a toolbox, a Swiss Army knife of physics and chemistry that generally applies to a broad range of reactor systems. So we have thermal hydraulics models in MELCOR. We have fuel thermal mechanical response models in MELCOR that are not just specific to light water reactor fuel assemblies, but have obviously been applied to triso particles, triso pebbles. Beyond that, we have models that very flexibly and can be adapted relatively easily to understand the degradation of fuel as it overheats and loses mechanical or structural integrity. Beyond that, we have models developed to understand ex-vessel damage progression. That is things like core-concrete interaction, or more colloquially known as the China syndrome, if you will. We have, but those models have a certain generic nature in terms of understanding heat transfer, be it the spreading of debris and containment, the interaction of that debris with water, that in a sense has a generalized applicability to other systems, and I'll just note that in a little bit. We also have models, a very generalized modeling capability in MELCOR with respect to assessing the fission product release and transport. So we have a generalized sectional model to look at the actual transport of, if you will, particulate material in fluids, be it liquid state or vapor state. And finally, we've actually added, in prompting originally from the NGNP days for looking at the pebble bed modular reactor, the capabilities to understand or assess reactivity effects and their implication on performance of a reactor system under accident conditions. As part of going through Volume 3, one of the things that we did was we looked at each of the reactor systems, each of the reactor concepts that we needed to look out to understand better and to put modeling capabilities together for. We did essentially a gap assessment, looking at existing MELCOR capabilities and looking at the types of modeling gaps that we would need to close in order to deploy MELCOR to assess these types of reactor systems. There are a range of if you will, things of relevance to MSR. I just provide this for illustration specific to an MSR system, a liquid-fueled molten salt reactor system. Obviously, there are things like physical properties, heat transfer coefficients, etc. A lot of those are gaps that primarily focus on the need to validate the models we have in there for this specific application. But then there are a number of phenomena related to the actual transport of fission products in these systems. And that's fallen under a lot of our development efforts for what we call the molten salt chemistry model. And then finally, there are actually, in the last two areas, there are a number of considerations that we've kind of added to the plate through some of the discussions ongoing under the molten salt reactor campaign. In particular, one of the last two are items that in discussions with Larry we thought might be necessary to look at accident scenarios where you actually have a salt spill into the reactor confinement. So we have to look at phenomena there like potential flow of molten salts out of reactor vessels, which could include or require us to consider things like freezing in flow paths and openings. Ultimately, we also have to apply and look at the release and the spreading of these molten salts on a reactor confinement floor, as well as the interaction of that molten salt with any water that might ingress into the confinement and interact with that molten salt. A lot of the models that I was putting earlier that we have for concrete interaction for ex-vessel behavior actually have aspects of their physics that we can, if you will, port into this application nicely. So I just wanted to note that from the perspective of the physics toolbox nature of MELCOR, if you will, and the breadth of physics capabilities, and how we're, if you will, porting that physics broadly. When we look at molten salt reactor systems, sort of more generally, be it a fluoride salt-cooled high-temperature reactor with triso pebbles or a liquid-fueled molten salt reactor, these are the types of physics and chemistry that we focused on. Obviously, we've added molten salt as a working fluid, so by analogy, we've kind of like added the steam tables, if you will, for molten salt. We've enhanced and made some modifications to our capabilities to look at fission product release in triso-fueled systems, as well as the transport of fission products in liquid phase systems that is in a molten salt or potentially in other types of fluid. fluids. And we also have extended our reactivity modeling, our simplified neutronics modeling, to incorporate point kinetics for a fluid-fueled system. I wanted to dive in and just illustrate some of the models that are specific to the range of molten salt type systems out there. As I noted earlier, we made some modifications to assess and understand, to better represent release of fission products from triso fuel. We've introduced into MELCOR a generalized model to essentially treat the diffusion of fission products through the complicated or through the more complicated triso particle structure, and then ultimately also to treat the diffusion of radionuclides through the graphite of the fuel matrix, if you will, or the pebble, if you will, in the triso. Oops, I hope this is going to pop up. And in addition to that, we've also, as I've been alluding to, Fred's been working consistently on adding additional capabilities to look at the transport of fission products, be they resident initially in the salt or released into the salt from triso. This is a generalized fission product thermochemistry model that we've added into MELCOR. It's actually, it's quite an exciting addition that we've made. The model that we rely on is that we are actually using, as Ted was discussing a bit earlier, we're actually utilizing the thermochemical databases to understand, if you will, to drive an understanding of the thermochemical state under different pressure and temperature and concentration conditions in the molten salt. We use the thermochemical database in conjunction with the Thermochimica code, the Gibbs energy minimizer code that Marcus Piro at Ontario Tech develops. We use that to essentially at each time step develop an equilibrium solution for this mix of material, of components in the molten salt, to get an understanding of what the solubility of fission products in the salt are, as well as what their vapor pressures are. Those vapor pressures then, if you will, act as a potential energy, if you will, that can lead to or promote more or less vaporization from the salt. The underlying thermodynamic database that we've been focusing on is the molten salt thermal database that Ted was discussing earlier, and that's going to be one of the primary databases, obviously, that we apply for molten salt systems. Based on the molten salt reactor experiment, fission products that are in the salt are actually divided up into a number of components. They can be soluble fission products, that is, they're kind of dissolved in the salt. They can be, if you will, colloidal, insoluble fission products that are in the bulk salt. They can also be insoluble fission products that have migrated to an interface between salt and atmosphere. And they can also be colloidal particles that have, if you will, deposited on structures. Finally, we also consider vapor phase fission products, things like krypton, etc., xenon, and their transport. And each of these components in the molten salt, really, we essentially treat the underlying dynamics, think of it like a chemical network equation with various mass transport rates. And we're really solving, ultimately, to solve the overall system and where the fission products are going, what form they're in, whether they're in the liquid, whether they're in the gas phase. We're really at a very basic level solving essentially a set of rate equations like you would kind of see in chemical network type analyses. For molten salt reactor systems, we've also very recently, Brad put this in recently, we've also added in point kinetics with considering fluid fuel advection. And so we treat, if you will, the advection of molten salt through the core, into the loop, and then back into the core. What I'm showing here is on the right side is a graph of a recent benchmark we did, where we actually compared the MELCOR simulation of a zero power pump coast down transient at MSRE, we actually compared, if you will, the negative reactivity addition that we needed to maintain the system at constant power with the MSRE data that we had, and we as a basic benchmarking of this initial model. And it captures both our hydrodynamics modeling as well as our reactivity modeling, which is why I like it as a nice, straightforward example of some of our overall capabilities. We have also demonstrated a lot of this work on, in particular, as I was saying earlier, the FHR UCB Mark I reactor system. We've developed a reference plant model for this system that comprises both fuel, reactor core, reactor system, and reactor containment. It's an integral system model to basically allow us to do and demonstrate integral plant response modeling capabilities. We've developed detailed models of the reactor core and vessel, the decay heat removal system, the DRAX, as well as the recirculation loops. We've put in a relatively simple model of containment with a few nodes. The overall containment structure that we decided on and assumed was something akin to a BWR Mark I from the reactor building from the perspective of leakage rate to the environment. We essentially just assumed a 100% volume per day at 0.25 psig leakage to the environment, typical of BWR Mark I's, to get us essentially, and all of this essentially gets us an integral plant response model. We've applied this actually to a range of scenarios. We looked at an anticipated transient without scram, using 3 DRAX. Obviously, this has some really interesting effects where we're actually looking at a number of reactivity feedback effects here. In this scenario, the salt pump shut off. The reactor does not scram as typical for Atlas. And then the secondary side heat removal stops. Obviously, we rely on DRAX for some level of heat removal from the system. However, the reactivity effects, there's actually a relatively large negative fuel temperature feedback reactivity that initially responds, if you will, to help begin to pull down that power. And we actually see in this scenario the power being pulled down quite significantly. And to essentially get the entire scenario, we actually, as part of doing this, we actually had xenon negative reactivity effects to MELCOR to understand the entire transient. And so we're actually in this reactivity transient an integral plant response transient, capturing fuel temperature feedback effects, xenon effects, etc. And then looking at effectively how power in the reactor core balances and reaches a point where it effectively balances with what the DRAX system can remove. So this was an interesting coupled integral feedback scenario with MELCOR, really just primarily looking at plant response. We've also done the more traditional station blackout scenarios. We've looked at a range of behaviors in these station blackout scenarios, looking at essentially a range of degraded DRAX performance. And finally, we've also demonstrated and essentially kicked the tires in these MELCOR simulations, looking at the transport of cesium and cesium fluoride within the molten salt system and released to the overlying gas layer of cesium and cesium fluoride. And this has kicked the tire, if you will, on the capabilities we've added with the molten salt chemistry model. And with that, I will turn it back over to you, Dane. Thank you so much.
Thank you for the presentation.
Thank you for your attention.
I think we have one question in the chat coming from Gus from Kairos. He's asking, can you expand on how the transport of insoluble fission products is treated in MELCOR? Are the vapor pressures of pure matter species applied, or are they considered part of the solution? Okay,
so insoluble fission products are our fission products that we are not soluble in the solution. And so we have those mass transfer rates out of the molten salt are treated separately, if you will, from our overall Gibbs energy minimization, specifically for looking at things like solubility and vapor pressures. We have separate mass transfer rates. We haven't exercised those specific capabilities yet. We focused actually on the cesium fluoride because of the importance of those fission products. So we primarily only exercised right now in our demonstration calculations the essentially the vaporization as a function of temperature of particularly interesting fission products that are normally soluble at lower temperatures in molten salt systems like cesium and cesium fluoride. We actually are beginning to apply this based on some work being done in collaboration with Ontario Tech to exercise against iodine as well, and looking at things like the beryllium iodides. Okay. Do you have any expectation for the date of release of this version of MELCOR? Okay, thanks. I think that's the next question. Sorry about that if I missed anything. We are planning in the next month or 2 months to essentially have this version of the code released as our, if you will, 2021 code release.
Thank you, Dave.